Okay, so in 20 slides, I want to explain probabilistic context-free grammar called PCFG and the CKY algorithm. Some people say CYK, so this doesn't matter, it's just three names. And so a review of context-free grammar. So N is a finite set of non-terminal symbols, and sigma is terminal symbols, like the words in your vocabulary. R is a finite set of rules. For example, here. So I will explain these things. I have explained these things in previous lecture. So we can say that S is distinguished start symbol, and what else? There we have some rules. X goes to Y1, Y2. This is binary because Chomsky likes that, but it has a deeper meaning. Why it is better to be binary. I've seen some Chinese articles in syntactic parsing. They use more than one, like this, but their approach is they are not taking advantages of something that you will see in future. So PCFG, context-free grammar, now it's probabilistic, because the probability that this goes, it depends on, for example, it could be 90% that this rule occurs. Another 10% could be for another rules. So that's why the summation of them should be 1. And so if you multiply these rows, you get the probability of a PCFG, probability of a tree. So the probability of a tree, so it is you can prove it that the probability of a tree is just this, the multiplication of all of these probabilities. So Q is the conditional probability of choosing the rule. Alpha goes to beta. And so let's say you have some graph. So you have the probability of this. You multiply all of these things. You have the probability of this tree. So this is the probability of this tree. So your grammar are like this, but now you have probabilistic because VP could be anything, and if you sum these, it's just 1. The probability of all of them, the summation is just 1. So it's a probability, and you can count it and see what is the probability of each one, but that's the initial point. You can use other techniques. In the last lecture, I will talk about inside-outside algorithm. But first, think about that. These probabilities. You have the corpus, and you just count them, and you have these probabilities. So the lexicon is like this. Determiner goes to that. It could be A, it could be the. Noun could be book, could be flight, but each of them has different probabilities. Verb could be book, include each of them is kind of probabilities. So in lexicon, you're connecting them to some pre-terminals. You're connecting to your terminals to pre-terminals. And the PCFG, as I said, the probability of a parse tree over all tree, but now the probability of R parse tree, for example, a sentence could have this tree, could have this tree, or any other tree. But what is the probability of this? What is the probability? If you sum the probability of occurrence of this and many other things, they could be exponential, they sum to 1. And so we will find a way to define a distribution over parse trees, P of tree, such that for any tree in your trees, the probability is positive, and also the summation of them is 1. So to calculate the probability here, for example, we say the probability of going the rule S to NP and VP, this probability times the probability of going from NP to DTNN times this, times the probability of DT go to there, times the probability of NN goes to dog, times the probability of VP goes to VI, times the probability VI goes to slips. So if you multiply all of these probabilities, you get the probability of this tree. You get the probability of this tree. So a simple PCFG could be like this. You have some words, and then some symbols, and you just count and then you will observe that the probability going from VP to VPPP is just 20%. So the Chomsky normal form, as I explained before, is a context-free grammar is in Chomsky form if for each rule it takes one of the two forms. So first of all, it's binary. It goes to two things. And X goes to where X is N and Y1 is N and Y2 is in N. And also X goes to Y where X is in N and Y is in your terminals. So transformation of a CFG to Chomsky normal form. This is a really good paper because sometimes you just need to use a trick in order to create a normal form so that all of our algorithm could still work. So deriving PCFG from Penn WSJ tree bank. So as I said, we just count the number of the rules and we normalize it. So this is the probability. For example, it has been seen that NP is seen 105 times in our corpus. That this rule is seen 105 times in our corpus. But this VP is seen 1,000. So if you divide it by the probability of your head, then this is the probability of this rule. So what if we have no tree bank? So welcome to unsupervised training world. Without a tree bank, we can use the inside-outside algorithm to estimate probabilities by randomly initializing probabilities, computing the parsers, computing expected counts for each rule, and we re-estimate probabilities. So first we assume that we know the probabilities. Then we compute parse and we compute expected counts for rules. So many of the formal properties of probabilistic context-free grammars were first worked out by Booth, 1969, proposed the inside-outside for unsupervised training of PCFG probabilities. And we always use CKY, so it's not unusual. Use CKY style parsing to compute inside probabilities. So they use CKY algorithm for just inside probabilities. And we find what is the most likely parse tree for a sentence. As I said, for each sentence we can have lots of trees, but which one is more probable? Because the other one are just ambiguities, are not what a person is talking. So it's not, they're ambiguous, and just one of them has the intention of the speaker. So what is the probability of that? So we use a dynamic programming algorithm called CKY, or some people say CYK, for this problem. So it's just three names. The CKY algorithm we present applies to a restricted type of probabilistic context-free grammar, a PCFG, which is in Chomsky normal form, while the restriction to grammars Chomsky normal form might at first seem to be restrictive. It turns out not to be a strong assumption. It is possible to convert any PCFG into an equivalent grammar in Chomsky normal form. We will look at this question more in the homeworks. So we don't use brute force to find the most likely parse tree, because it's very costly to do that, and it's not feasible. It's intractable. The cost is exponential because you have lots of these trees. You cannot find the probability of each of them and say, okay, this is 85%, this is more than other. For example, this is very small probability, and so on. So the brute force doesn't work, as usual, in any problem in computer science. So this is what we do for CKY algorithm. Once you know that if you define this variable, then everything is enough. Because your answer is this. If the P1 to n, we want to know this, first the trick of dynamic programming, the beauty of dynamic programming is just creating recursions. So in order to create a recursion, good recursive style approach, we need to know the constituents of that. What are the relations between the constituents of that? For example, going from I to j, for example, here, example pi from 3 to 8, if you go from saw to telescope, this is what is the maximum probability of tree, but your tree is just from this. So, for example, ignore the rest of them and just look at this span from 3 to 8. So this is this variable. And then we use this to answer, we use some recursive relations, recursive equation to reach to this one. And what we do that, how we do that is like this. So the recursive approach says that the ij span, you can split it into the ij span, you can split it into from q, cut it from q, then you have two spans, this span and this span. So we have two spans from x to yz, from I to s. S is called the split point. So this is the first span. This is the second span. The first span is y, and the second span for z. So you can. This is the trick that we use. We relate the pi of I and j span to the I and s and sn. So if you go from bottom to top, then you can recursively do this several times recursively, and you answer the biggest constituents, which is the answer to our question. So this is the CKY algorithm. Look that L is the length of the segments. And for each of them, you not only are just updating your variable, you go from smaller constituents to larger constituents. And just like in reinforcement learning, you also record and save your store your back pointers as well. Otherwise, what's the problem? What's the point? So the back pointers allow recovery of the argmax of this probability of a tree over all trees that you can imagine. So the time complexity of CKY, unfortunately, is high, but no problem. I mean, the number of words is not that big. For example, number of words of a sentence could be, for example, 20. N could be 20. So the biggest sentence, for example, you could imagine. And capital N is a number of rules. You don't have lots of rules, at least in CFG, you don't have lots of rules. But in CCG, in combinatorial categorical grammar that we use in semantic parsing, it is exponential. The number of rules is exponential. That's why we use some tricks in order to say that simple rules are more probable, and that's why we cut it off. And so this is the number of Y or Z, and that's why this is the order of complexity, time complexity. And so you can compare the Eisner with the CKY. This is a homework for you to think about this. Because the work of Eisner goes back to 1960, I think.